A long uniform rod of mass m and length L is supported on the left end by a horizontal axis into the page and perpendicular to the rod as shown above. The right end is connected to the ceiling by a thin vertical thread so that the rod is horizontal. The moment of inertia of the rod about the axis at the end of the rod is 1/3 ml squared. Express the answers to all parts of this question in terms of m, l, and g. Part A. Determine the magnitude and direction of the force exerted on the rod by the axis. So we're going to want a free body diagram, or at least a vague free body diagram-like thing. So there we go. What forces act? Well, of course, there is the weight of the rod at the center. And then there is the force from the axis. And then there is the force from the thread. And we want, of course, this one. So there is no rotation. It's being held horizontal, which means I can pick rotation on any point that I want. I'm going to pick a kind of odd point. I'm going to pick this point to be the rotation about which I draw things. And I have, of course, the fact that alpha is 0, because nothing is rotating. So we can just set up the torque around, and again, this odd point, and we can figure out what that, set that torque equal to I alpha. So we have something like the torque due to the axis plus the torque due to gravity about that axis, although I'm going to note that it's in the opposite sense, so I'll put a minus sign there. And that has to equal I alpha, but alpha is 0, so that equals 0. A given torque, any torque, is R perpendicular times F. Luckily, our lines of action here are vertical and therefore perpendicular to the rod, so all that matters are the distances of the rod. And so I say, well, this distance is given as L, and this distance is clearly L over 2. So I end up with something like L times the force of the axis plus, and then we have the negative. Gravity is located only L over 2, and we have mg. And then over here we have this equal to 0. And it's pretty easy to see from there really rapidly that F axis equals 1/2 the weight of the object. To be precise and strictly speaking, I should be using their symbols, so I will switch over here and say this is now mg. So we do that. Notice this is a result we had done in class, and people often remember, oh, well, it has to support it by being half the weight, but you have to show that. You can't say that because it's not always true. It's because this thing is centered and supported at both ends and so on. You could probably get away and impress a reader if you argued it by symmetry, but you have to say something. You can't simply assert that the thread and the axis have the same forces. That will not get you any, or at least not very much, of the credit. Okay, the thread is then burned by a match. For the time immediately after the thread breaks, determine each of the following. Part B, the angular acceleration of the rod about the axis. All right, we're still going to want our picture. So there we are. And we still, of course, have the weight pulling downward, Fg. And we have some force from the axis pushing up. I'm going to call it Fa star, because it might be different. But most importantly, we do not have this tension anymore. And because of that, the thing is going to rotate. The bar is going to do something like that with acceleration I'm going to call alpha. And alpha is what we're looking for. So yay for that. We're going to do a similar kind of analysis. We're going to do a torque analysis, but this time we can't cheat by having something equal to 0. So now I'm going to pick this point, the axis, as our point. In general, if there really is a rotation, you should pick the center of that rotation as the point from which you compute torques and accelerations and so on. So that's what we're going to do. And we're still going to fall back on the idea that the torque is I alpha. So now our torque is entirely gravitational, so tau g, and that should equal I alpha. But tau g is not so bad. We again see that by the symmetry, this is L over 2 as well. And so we end up with L over 2 times m times g on one side. And that equals the given rotational inertia, which is 1/3 ml square times alpha. A couple of convenient things happen, as they often do. Notice that the mass cancels. That's nice. And 1L cancels, leading us to eventually get the final answer here, which is that alpha is g over 2 over 1/3 L, or 3/2 g over L. And that's our angular acceleration. Part C. Determine the translational acceleration of the center of mass of the rod. So we look at our picture here, and we have the pivot here, and we know that the center of mass is going to accelerate that way, and we know that it will track out, or would track out if it could do complete one, a whole circle. And so we know that that acceleration is r alpha. And that's sort of a general thing. For our particular thing, r is, well, once again, the circle it tracks out has a radius which is L over 2. And we just found that alpha was 3/2 g over L. So putting all that together, our acceleration must be 3/4 of g. So the object is falling, but it's not in free fall, which makes sense because, of course, it's being supported. Part D. Find the force exerted on the end of the rod by the axis. Perhaps no surprise, but once again, we're going to draw our quasi-free body diagram, and we're going to say that our forces are Fa star pulling up and the weight pulling down, and they produce an acceleration downward, which is 3/4 g. So, well, the center of mass, remember, is a point that acts as if all the external forces acting on the system were acting at that point, and its position evolves as if it were a point particle subject to those forces. So our center of mass is subject to two forces, the weight and the axial force. I'm going to take downward as my positive direction because my acceleration already points that way. And so my second law, which starts off as that F net is ma. And so for our picture, we have minus, take it back. We have Fg, and then we add in Fa star, but it's pointing the wrong way, so put a minus sign. And together those should equal the mass of the system times the acceleration of its center of mass. And then we can just start substituting in. So we have mg plus minus Fa x star, which is what we're looking for, equals m times 3/4 g. Then we do a little bit algebraic legerdemain. We bring this over to this side and this over to this side, and we end up with Fa star is mg minus m 3/4 g, which is pretty easy to process, being in the end 1/4 mg, or 1/4 of the weight. Notice that when it was being held up at both ends, it was a half of the weight, but when we cut the string, it drops instantaneously to 1/4 of the weight, which is kind of a weird thing all by itself. All right, then the rod rotates about the axis and swings down from the horizontal position. So we're not in the immediate after, but the far after. E, determine the angular velocity of the rod as a function of theta, the arbitrary angle through which the rod has swung. So let's, as usual, draw our picture. let's draw like the original bar is like that. And then now it has swung down in sort of a circular arc. Well, actually a circular arc. And through some angle. And so I'm going to define this as theta equals 0. And now the center line has swung through some angle. And they would like to know what is omega at that angle. So based on previous years having given this problem, a very tempting thing to students is to say, oh, well, we're going to use something like omega squared equals omega 0 squared plus 2 alpha delta theta, i.e. our kinematic equation, because, you know, we can set this to 0 because it starts from rest, and we're looking for this, and we can even maybe take this thing and set alpha to, you know, I over tau, and then move forward. This does not work because alpha is not constant, right? Alpha is I over tau, but tau involves something like L over 2 times sine theta. Yeah, something like that. Times mg or something like that. It's some horribly non-constant thing, and so that's no good, and we can't do that, which is a little sad and depressing because, after all, kinematics is easy. We've got to think, what can we do that would allow us to talk about velocities if we can't use kinematics, if the forces are changing, and that is something custom made for an energy analysis. So instead, we're going to say that the object starts from here, y equals 0, and then later on, the point we're talking about, the center of mass, which is what we care about, has descended a distance, some h, right? And so our energy at the start was 0, and our energy at our location is mg times minus h. Why minus h? Because our gravitational formula treats y as positive upward, and we have gone down some distance. And then, of course, we also pick up a kinetic energy term, which is 1/2 I omega square. Notice that we have both the center of mass having an energy, and we have the inertia contributing an energy. So we go from there. We don't have to include what might appeal to you, which is sort of a 1/2 mv square, because that is already included in this term. So there's a gravitational energy, we have to worry about the center of mass, but for the rotational energy, we've already included the center of mass's motion in that by computing I. We have most of these variables already, either as givens or things we found, but we don't have this h, so I've got to get that in terms of what we do have. So we imagine that the center of mass, which is located some distance from the axis, it's of course L over 2, and then it swings down through to some angle, moving along a circle, and so this is also L over 2, having fallen through the angle theta. But what I care about is this height, the height through which the center of mass has fallen. And we know for gravity, I don't really care about the distance it's moved over. I only care about how far it's fallen. So we can say from there pretty easily that h over 1/2 L is the opposite over the hypotenuse, so it is the sine, which tells us that h must be 1/2 L sine theta. From here on out, it's pretty simple. We're going to say that the energy at the start equals the energy that I have. The energy at the start is, of course, 0 kinetic because it's released from rest, and zero gravitational because I have picked my 0 point to be there. You might find that counterintuitive and put it somewhere else. It's a little weird to start at 0 and then be going down. But no matter how you do it, you're going to be doing some rigmarole that gets us to the same place. All right, and then the kinetic energy, as it's falling at the moment we talked about, is 1/2 times I omega square plus the potential energy, which is m times g times minus h. So then we just start substituting. So we say that our 0 is 1/2 of 1/3 of ml squared times omega squared, and that is plus minus mg L over 2 sine theta. Then we start looking at things that, we don't care for anymore. So we say, hey, look, the m's cancel out, which we're used to. And also, the halves cancel out, which we're not as used to, but it's kind of nice. And one of the l's cancel out. So we end up with bringing, let's say, this guy over to the other side, or vice versa, however we want to do it. We end up with something like 1/3 L omega squared, and that equals g sine theta, which allows us to eventually say that omega is 3g over L sine theta, all square rooted. And there we have it, all 5 parts.